The second case study is a deacidizer column. The column is able to process a feed for 500 kilotons per year propylene production. The system also has a small overhead as well. The bottom product accounts for 90% of the feed. Off-gas is removed from the overhead and sent to the fuel gas system. The column was identified as the single largest relief source of the plant, which is 840 tons per hour relief, which governs the main flare system design, including the header sizing, knockoff drum sizing, and the flare stack sizing. Based on this huge relief load estimated by the steady-state method, multiple PSV are required with a set pressure of 3,400 kPa. As shown in this sketch, the deacidizer stripper is coupled with a rectifier and associated overhead system. The stripper has an air cooler condenser and reflux from the rectifier sump. Two step-in reboilers installed in stripper bottom sump to be modeled as a kettle-type heat exchanger. Rectifier has a propylene chilling condenser and reflux from a liquid receiver. PSVs are installed at column top piping section. Total power failure and partial power failure are also studied here, as they are identified of having two largest relief loads by steady-state method. Upon the total power failure, the feed stops, both stripper reflux and the rectifier reflux stops as well. Bottom products continues on level control and eventually will stop when the columns runs dry. Off-gas is assumed blocked as the fuel gas compressor is off. Both stripper condenser and rectifier chilling condenser are lost. Heat input to reboiler continues with the thermal limitations as the steam is assumed to continue its normal flow. Reboilers are modeled as a UA exchanger rated with a fluid circulation rate, which will be limited by the reboiler system hydraulics during the upset scenario. The partial power failure case is assumed to have the similar upset to total power failure scenario, except that the feed continues as the feed pump is assumed working on partial power failure. 50% of the electric fans on air cooler are still available for cooling the overhead vapor. Off-gas continues to fuel gas system with a pressure control valve on fair last position, assuming the downstream fuel gas system still operating normal. This is a relief profile of the deacidizer column during the total power failure. The left y-axis is the relief load in kg per hour, and the right y-axis is the pressure at column overhead in kPa. The red line represents the relief load over the time after the upset initiated, and the blue curve is the system pressure changes recorded during the relieving process. Dynamic simulation indicates it takes about 11 minutes for the system to reach the PSV set pressure, which is 3,400 kPa. The peak relief of 288 tons per hour is identified at around 20 minutes after the total power failure event initialized. Since the feed stopped, The hot up liquid flow from the top tree section to reboiler where tips off, and the heat input to column will eventually stop. As a result, the relief will stop once the liquid hot up on all the trees start running aft. This is a relief profile of the deionized column during the partial power failure. When the partial power failure event initiated, it takes about 15 minutes for the system to reach the relief set pressure. The peak relief of 245 tons per hour is reached at around 33 minutes. Since the fade is assumed to continue in this case, the heat input from reboiler to column continues as well. As a result, the relief continues and eventually stabilizes with the fade continuing. The dynamic simulated relief loads are compared with the loads estimated by the steady state method for total power failure and partial power failure. For a 500 kilotons per year propylene production, dynamic simulated peak relief is only 1/3 of that estimated by steady state method for total power failure. On the other hand, about 50% reduction is achieved by dynamic simulation for partial power failure case. Based on the dynamic simulation, one R-size PSV is adequate to handle both total power failure and partial power failure upset. However, the loads estimated by the steady state method will cause for two PSV, one R-size and one T-size. As we mentioned to the relief from the deionized column determines the dimensions of the flare system. The reduced relief loads by dynamic simulation will have a significant impact on the flare header sizing, flare knockoff drum sizing, as well as flare stack sizing. The potential savings in CapEx can be tens of millions of dollars, not to mention to the benefit on acoustic-induced vibration issues of discharge line and flare headers due to these reduced relief loads. The reduced dynamic relief loads by dynamic simulation is attributed to the listed advantages of the dynamic simulation. Here, dynamic simulation considers limited liquid hot up within the system. It takes credit for system volume. It simulates the hydraulic and thermal limitations of the system during the relief. Particularly, dynamic simulation indicates the relief is subcritical, where the steady state modeling assumes supercritical relief. Here is a block flow diagram which summarizes the column relief calculation hierarchy and offers a brief guide for when, where, and which method should be used for column relief analysis. The choice of the calculation method depends on the nature of the project, complexity of the system, and the impact of the transitional changes. As indicated by the passes on the top section of this diagram, the unbalanced heat method is preferred for the grassroots design for simple fractionation columns. It typically generates conservative relief loads and leaves a good margin for PSV and the flare system design, which is beneficial for the plant to debottleneck in the future. For the system where unbalanced heat method is not applicable, like stripper or stabilizer, The steady-state simulation provides an alternative way for a quick and simple solution. As we follow the paths in the middle section of this diagram, it can be either a grassroots project or a revamp project. Since the conservative assumptions are used for any transitional changes, it represents the maximum potential relief moment of the dynamic reliefs. Therefore, the relief loads by steady-state simulation are still considered to be conservative. As shown by the passes on the bottom section of this diagram, dynamic simulation will offer a rigorous and more accurate approach for column relief estimations. Although the method itself can be used in grassroots design, there is nothing wrong to use it. But the advantages of dynamic simulation are pronounced for the brownfield projects, where the loads estimated by the steady-state method can exceed existing PSV limits or flare limits. To summarize, here is when and where dynamic simulation should be used. When the column system is not suitable for unbalanced heat method. When unbalanced heat method or steady-state simulation calculated loads exceeding the PSV or flare limits. When the impact of the transitional changes become important for relief loads, for example, the hydraulic or thermal limitations become significant during the relief. The relief loads estimated by the dynamic simulation are typically less than the loads by statistic method, not always though. Dynamic simulation is a promising tool to ensure safe design and to save project cost. That is all of my talk today. Thank you for listening. Now I would like to hand over to moderator for Q&A section. Sabrina, back to you.
Thank you, Harry. We have had a lot of questions come in. And so for the first question, I'd like to ask you, besides column relief analysis, what other applications of dynamic simulation can you recommend?
In addition to column analysis, dynamic simulation can be used for many other process validation and evaluations, such as unit emergency depressuring, control safeguard evaluation, exchanger tube rupture safety checking, the compressor anti-surge analyze, and the plant optimizations. A paper of mine to be published in Hydrocarbon Engineering next month will give you a good example of plant configuration optimization with dynamic simulations. In that paper, we used dynamic simulation to evaluate the stability of the high-pressure steam system for an LNG plant. We simulated a different design of the steam producers, which are boilers and heat recovery steam generators. And we modeled the different configuration of the steam users as well, which are HP steam turbine and LP low-pressure steam turbines. So we tried several different upset scenario of the design. For example, we let one boiler strip and the other boiler were ramping up. And we assume one major steam turbine trip and let the boilers to ramp down to ensure the selected design is robust and it can provide a stable steam supply even during those upset scenarios. The results actually has demonstrated that the dynamic simulation is a very powerful tool to identify the best steam system configuration in early stage engineering, which can capture significant savings for the project. Back to you, Sabrina.
Thank you. So kind of returning to an earlier portion of your presentation, the unbalanced heat method. The question is, when we use the unbalanced heat method for column relief valve during pump around failure, what will actually happen within the column trays? Should we assume that all the trays above that will become vapor, or will it start to flood inside the column?
It depends. In case we modeled, because we assume that the feed stops, right? So there is not feed coming into the column. So once you pump around pump fails, basically is whatever the liquid hot up left on the trees will start to flow down from the top section to the bottom section. So what you will see from when you're running dynamics, you will see your top trees will start to dry out one by one from top to the bottom. And depends on the running time of your simulation there. The vape, it's still the vapor liquid equilibrium based on the equation of the states, because we're still putting heat from the reboiler into the column. So you will see still the two-phase flow over those trees, until the trees running dry from top to the bottom. That is the situation is going to happen. Back to you, Sabrina.
Thank you. All right. Would the dynamic simulation strategy be valid for reactive distillation systems too?
Yes, it were. Yeah, we actually did that kind of dynamic simulation for a client for HDS column reactions system. But you do need input from the licensor in terms of the reaction kinetics changes during the upset scenario. For example, what will be the reaction heat changes when the system pressure goes high? What will they change when you stop the feed? And the fresh reactant will not be available in these cases there. So you need to make some assumptions based on the input information from the licensor. You do need some supporting from there. But of course, it is once you have those information and you make conservative assumptions, you are able to do dynamic simulation on those systems. And the results, what we did on that column, this turns out to be pretty good. And the results is very helpful for the project to make good decisions there. Thank you. Back to you, Sabrina.
Thank you, Harry. Can you simulate a unit total shutdown in dynamic simulation without affecting hydraulics? For example, a negative delta P during the SIF actuation?
You can always simulate it upset case as long as your assumptions for that upset case, the base has been made based on the good engineering judgment basis there. That is actually quite similar to the cases we studied for the hydrochloric unit, like a compressor emergency shutdown and end up with a settling aft pressure. In that case, it's a totally shutdown of the unit, and the pressure will eventually balanced within the system, end up with a settling aft pressure there. Yes, you will see the flow the backwards from some section of the unit based on the hydraulics profile. You see the pressure surge here and back off to the flow to the other section there. You'll see the pressure up and down a bit, surge and comes down, but eventually the system will balance by itself. Just as I mentioned, like compressor shutdown, setup pressure there. The system will balance by itself. But the backflow does happen. Back to you, Sabrina.
Thank you. So can cooling due to a natural draft at the air coolers be considered for a power failure scenario in the dynamic simulation?
That's a good question. Yes, it can. Based on the API 521 guidelines, the natural draft cooling effect that credit can be taken. And the guideline is say is about 20 to 25% of the normal duty. But in my experience, you'd better to run that natural draft effect in HTRI runs under that offset scenario. So that will give you a ballpark the how much duty you can gain for that natural draft effect. By my experience, that the credit of that duty you can take in is really depends a lot of factors, especially the inlet temperature of the to the air cooler and that offset scenario there. So it's my suggestion were run the HTN run to get the natural draft effect, and you do that simulation to get the equivalent duty in your dynamic model. Yes, you can do that. Back to you, Sabrina.
Thank you. So you mentioned during your presentation that relief loads predicted by dynamic simulations for columns are typically lower than the loads estimated during steady state methods. Can you give us an example where that dynamic simulated relief can be higher than the loads simulated by steady state methods?
That is an interesting question. Yes, most of the time, you will have the lower relief loads predicted by dynamic simulations as compared to the loads by steady state method. However, there are cases where dynamic simulated loads can be higher than the loads by steady state method. I'll give you an example. We just did a dynamic relief analysis for a deprobanizer column. In that particular case, the flow control of steam to reboiler is cascaded with the level control of the column sump. During the upset scenario, like column overhead condenser failure, the increased pressure within the column will result in a substantial condensation of the C3s, which is propylene or propanes, during that initial stage of the relief. As a result, the liquid level in sump will increase. So the steam flow control will respond to the increase of the sump level to increase the steam to the reboiler. That will add more duty than the normal operation. So eventually, this will end up with a higher relief loads as compared to the load estimated by the steady state method. Because by guidelines, normal duty is taken in steady state relief calculations. In this case, the dynamic simulation has identified a potential relief governing scenario which was missed by the steady state method. Back to you, Sabrina.
Thank you. So was the dynamic model also used to check the minimum metal temperature in the columns during the scenarios?
Yes, you can do that, but we call it like a unit depression study. So you need like a special tools to doing that. And as far as I know, that not much tools can provide that function there. And at this moment, there's a blue down utility you can use in HASIS. And you can use that one to the blue down depression system. That will give you a more rigorous predictions of the system. And because this is a complex system, and the tube metal temperature really depends on the heat transfer between the fluid and the mantle. and heat transfer between the outside of the air as well. So there's a lot of factors going on there. Yes, you can do it, but you need to some information or data to validate your model before you're using those results. Thank you. Back to you, Sabrina.
So what is the approximate time to develop a dynamic model? Can you give us a few examples?
That's a good question. Actually, the timing to do a dynamics study really depends on two factors. The one is how experienced the guy doing dynamics. This dynamic simulation does require some experienced skill for doing this. It does need accumulated years of the working experience in this simulation area. Another thing depends on the complex of the system you study there. If the experienced people doing the dynamic study, for example, if you just do a simple system like a pump station and a tankage, it takes about, in my experience, a couple of weeks to do that. For a column relief analyze, it can take like 3 to 4 weeks, by my experience. For more complex system like a hydrocracker unit depressure ring, in that case, you have more equipment getting involved. That takes about, say, 5 to 6 weeks to complete. And I want to extend this question a bit. Lots of the time when a project manager comes to me and asks me to do the dynamic simulation for PSV, they ask me, Harry, can you do a dynamic simulation for this PSV because it's not working for whatever reason, and give me an answer for next week? I'm sorry, I can't do that next week. I'm not a magician, but maybe I can do it, complete it in, say, 3-4 weeks if the data is all data available. Then how about 2 weeks? So we make a bargain. And sometimes we can reach a deal, sometimes we can't. So what I want to see here, if you make a plan for the project execution, please include the dynamic simulation in the scope of the work from the beginning of the project. So in that way, we can get the job done in a more elegant way, and you will have a smooth execution of the project. Back to you, Sabrina.
Thank you. All right, we have two questions similar. So it's around the dynamic modeling changes of state from the supercritical to subcritical. And so it's how is using dynamic modeling change the state of the system through the, as I said, supercritical to subcritical, the system design pressure. So is the relief pressure fixed? And are there other consequences or implications of these changes?
The relief pressure is always fixed in your dynamic model there. Sorry, the relief set pressure is always fixed, but the relief pressure is not. So the relief pressure really depends on how much relief is pushing to the relief valve. For example, if you have enough relief loads, which can push the relief valve fully open, and which is like in single relief, PSV relief, it's a 10%, 110% of set pressure. In multiple relief, PSV relief valves, which 116, 10%. So it can push to that high, all the way that high, if you have enough sustainable relief loss to push it. The highest relief pressure will be our pressure required by the APM 521 there, right? Yeah. So that's the dynamic simulation is simply just simulated those vapor-liquid equilibrium based on equation of the state, right? Based on the whatever the thermal package you are choosing, it simulates the equilibrium VLE is that maybe goes towards the critical, goes near the critical there region. But unfortunately, most of the time, once you get the critical, reach the critical, you will have the problem of the converging there. And in that area, you need to be careful and validate your data there. Your sacrifice finds some accuracy there. But fortunately, in our case, most of the time we still found our simulation is still under that supercritical region, which is a beneficial beauty of this dynamics. And because for the system, as an example I'm giving you, if you do the steady state modeling, you have to assume that fully open overpressure, which is either 110 or 116 overpressure there. That will bring you directly to the supercritical region if you do the steady state modeling. But if you do the dynamics, it takes whatever pressure it can reach, which is beneficial, because in that case, you may not getting there to the critical region. Back to you, Sabrina.
Thank you, Harry. Well, it looks like that is all the time we have for questions today. So we will follow up with any unanswered questions. We really appreciate all of you for attending today. You have been a very engaged audience, and it's been a pleasure being your moderator today. So next, we will be hosting our next webinar on Thursday, September 24th at 10 a.m. Central Time, when Kathy Chargay will discuss the latest and greatest in reactor affluent air cooler corrosion. So please keep in touch with your Fluor contacts, follow our social media postings, or head to the Innovation Builders page on fluor.com to register for future webinars. We appreciate your attention, and thanks again for joining today. We will send out a compiled list of the Q&As within a few days, and we will notify you when the webinar recording is available on fluor.com. So if you have any questions or require additional information, please email innovation.builders@fluor.com, and someone from our team will get back to you. From all of us in the Innovation Builders team, have a safe day. Thank you.